Okay, welcome back at the last session of today, and we will start with a talk by Patrick Doyle, and it's about knot dynamics. Patrick is from MIT, and he also works at the Singapore MIT Alliance for Research and Technology here in Singapore.
Thanks, Johan. So thanks for the organizers to allow me to attend the conference. It's really been great talks. So I'm going to shift gear compared to some of the talks in the last session, actually talk about more polymer physics and using DNA to understand some things about knots in a lot of different contexts. So actually a lot of the work has been done at MIT by Beatrice, and she's actually from Singapore and funded by A-STAR. So she's bonded to come back at the end of her PhD. All right, so to set the scale a little bit, knots are very old constructs. Okay, so you can find them in ancient Chinese scribes, etc., actually for recording events. Historians believe they predate fire, actually as the first instruments used by mankind. And we see them all over, right? From mariners to if you still have old-fashioned headphones, you shove them into your pocket, you pull them out, you're going to have a topological knot, okay? One thing I'll get back to is actually, we believe actually this effect of actually shoving an object into a tight spot increases the probability of forming a knot, okay? And we're going to use that to our advantage later on. And lots of macro scale objects will form knots. So this is Doug Smith's work. These are large fibers rotating in a box. You stick a fiber in a box, rotate it, and you plop it down on a surface. And through the projection of that image, you can prove that they're actually knots if you imagine joining the two ends. We've done similar things, putting fibers, for example, in shearing flows. We can carefully, with a sieve, take out the fiber and then show that what was initially unknotted becomes knotted. Okay, so shoving fibers, flexible objects into tight spaces will form knots. Jumbling them around will even make more knots. Now, at the molecular scale, knots are very important. So for example, if you tie a knot in a polymer, it will change the mechanical properties. You're more apt actually to break at the entrance and exit of the knot. And for a long time, actually, polymer theorists have been fascinated by knots and actually how they affect dynamics in polymers in many different contexts. So there's a very nice paper by De Gennes in 1984. It's a very classic De Gennes paper where he gets away with writing 2 pages of a conjecture of that, well, maybe some of the very long time scales you see in polymer crystallization is due to the fact that you have tight knots. And a tight knot can take a very long time actually to get off of a polymer molecule. Okay? And actually to this day, this idea, are there tight knots in polymers, has been something which has been very contentious. Knots are also sort of the foundation behind a lot of long time scales in polymer dynamics, where either within a chain or more probably within multiple chains, you actually get these frustrated, long-lived conformational intertwining of the chains. In DNA, knots have been studied, and you see them all the time. So the simplest knot one can tie is a trefoil, shown here. And we have all these entanglements happening in our body, and we have enzymes which will actually take 2 strands and relocate them. Johan's group has done some really nice work looking at the rheology of these effects. Okay, so our body knows how to knot and unknot, or change the topology. And it's been seen in capsids, actually, when you stuff the DNA into the capsid and look at the ejection, that actually you have a wide range of knots. And their simulations speculated that actually it's due to the fact, not because of any special chemistry within the capsid per se, but actually just the confinement in of itself leads to this large degree of knotting. And more recently, in biotechnology, so taking very long DNAs and shoving them through nanopores, we conjectured that we should be able to see knots on molecules. And in fact, not only that, but if we pull the molecule hard enough, we should be able to actually jam knots at the entrance of nanopores. And very recently, with Slaven Garaj, who's here at NUS, well, down the street in NUS in the physics department, we have a joint graduate student, and we've actually been taking large T4 DNA, putting them through nanopores, And we actually can discern through the signatures of the voltage drops different conformations of the molecules. And these are rather classical conformations one might expect, where basically you pass through in a single line, or maybe you pass in a backfold. But we see lots of conformations where we actually have these dips here, and we can actually quantify the amount of contour which is stored basically in this dip and infer something about a localized knot on the molecule. So these are quite intriguing that actually, as we're starting to sequence large molecules, we'll actually have a preponderance of knots, and they can affect the statistics of what we see. Okay, so what do we do? One thing we're going to show you about is single molecule experiments. So this is the large T4 DNA molecule. That bright spot right there is a knot. I'll show you how I actually make the knot and then stretch out the DNA. And I'd like to study all sorts of things about this knot. For example, how big is it? How does it move around? Does it move around? Can it move off the molecule? Does it move off the molecule by diffusing, or does it convect off the molecule, for example? Does it come off just in one step, or is it multiple steps to get off of a DNA? And you can imagine that this could be very important, because imagine I have a nanopore down here, and I'm trying to shove my DNA through it. I'd like to know if I can easily slide off that knot, or if it will get jammed, for example. Okay, so we just look at single molecules. So statistically, I could just hope that I'm going to see a knot if my molecule is long enough, but that can be a rare event. So I'd like to, put statistics better in my advantage. So I told you that if I shove a molecule into a tight spot, it's more probable to form a knot. So we found a very convenient way to do this with actually a slight oscillation of an electric field. So essentially what's happening here is that's an equilibrium DNA. I just do a slight pulse of 200 volts per centimeter, which is pretty common when you're doing electrophoresis. The frequency, it's not too sensitive to. And we showed in a series of papers that essentially there's an instability that will compress a polyelectrolyte. And so we compress the chain for a moment in free space, and we think actually the chain gets spun around a little bit. And what I've proved to you is actually this molecule actually has a knot in it. So if we watch it for a while, it takes a very long time to relax. It's a little maybe hard to see in this image, but eventually it'll actually poke out a couple arms. And if you watch it long enough, it'll actually go through a series of states where it's a self-entangled coil. When I turn off the field, it sort of springs out a little bit because of electrostatic interactions. But it has to disentangle from itself. The arms come out, and then eventually, actually, this knot has to disengage. And here's a whole bunch of different molecules at this intermediate state, and we always see this localized bright spot. Okay, so back at this time, we postulated that this was indeed a knot. Okay, but it's a little tough to prove from these sorts of experiments. So a nice thing to do would be to take this molecule and start to pull on it, and we can maybe more easily see the DNA knots. Okay, so before I do that, I'll just show you that indeed we've done simulations. These are rather simple mesoscale simulations. And if you just look at the top, which is the probability of forming a knot, indeed, this is a dimensionless basically ratio of how compacted my DNA is that we go to very high probability of actually forming a knot. And in the sort of experiments that we're doing, we're kind of sitting somewhere up here, where nearly 100% of the time that I oscillate my field, my molecule will have a knot. So I now have a knot factory, essentially, to study and make knots a single molecule at a time. So to be able to probe this molecule, I could put tweezers on my DNA, and we've seen lots of elegant examples of that. The problem is probably putting that big bead on the end of my DNA is going to preclude making a knot, right? So I want to have a handle-free method of making and pulling on my knots. So what I can do is actually use the fact that the DNA is charged, and I use a microfluidic device, which is a cross slot. And if I apply different potentials at these two exits and these two entrances, actually create a region where there's zero electric field right in the middle, and there's basically a tug of war. And this is a so-called planar extensional field. The nice thing is that if I design my device carefully, I can actually analytically write down what is the shape of that electric field and do a lot of pen and paper calculations to predict how my DNA is going to stretch. The other thing is, since it is a stagnation point, That's where I can actually bring in and trap a molecule and interrogate it. So here's an example of an unentangled molecule without a knot. So it came down. It's actually being stretched, and I can hold on to it for a while to study it. So when I put a knot in my DNA and do the same experiment, so here's for reference an unknotted molecule. Here's a highly entangled molecule. The same time is passing, right? You see that this molecule is clearly frustrated. If we're patient, it'll eventually start to disentangle, right? You'll see a series of blobs, and some of them actually persist. So for example, there's a knot, and I believe there's another one later on the molecule. Okay, so we can actually, if we're patient, form these compressed configurations and actually stretch them out. And now we have either a knot or a series of knots on the molecule that we can study. Okay, so a lot of funny things happen to this molecule and to knots. So the first thing I'll tell you about is actually a little details about how it stretches. So here's my device. And in terms of just how a polyelectrolyte, or actually a point charge, moves in this device, it's all defined by one parameter, which is essentially a strain rate. Okay, so for my known polyelectrolyte, which has a mobility, and my field, I can define this. So that's a time scale. The DNA is a competing time scale, which is its relaxation time. And so there should be a dimensionless group, which in rheology people call a Weisenberg number, which is just the polymer relaxation time times the rate of the field. So if this is big enough, the field wins and I stretch. If it's not big enough, nothing happens. Okay, so here's unknotted molecules, very classic things. And you can prove that basically this is like a first order phase transition. At a Weisenberg number of 1, you suddenly have a large stretch of your molecule. And together with that, if you look at the green data, you actually have an increase in fluctuations, which are all the signatures of actually sudden first order phase transition. So what do knotted molecules do? Well, I said that how you stretch here depends upon the relaxation time of the molecule and the field you put it in. What a knot is going to do is actually change the relaxation time of the molecule. Right? So if I have a stretched out molecule, here's the same molecule, I later put a knot in it, I watch it relax, and I can do this actually multiple times to gain statistics, but I'll just show you the envelope of relaxation. So here, for reference, here's the unknot, here is the knot, and you see I actually relax faster. Okay, so actually having a knot makes my molecule somehow come back to equilibrium faster. So the relaxation time is going to be smaller. And actually, in my knot generator, I can generate lots of different knots, and statistically, they're always different. Okay, I don't have control over that. But what I can measure is actually how much of the contour of my chain is basically stuck inside this knot from the fluorescence. And so I make all this family of knots, and I measure the relaxation times, reference to the unknotted state. And you actually see it's not a slight effect, so we can really decrease these relaxation times by a factor of 2. And a simple idea of what's happening is basically that you're freezing out degrees of freedom within the knot, and you're effectively making the chain a little bit shorter. And if you buy that argument, you can go through some scaling arguments, and more or less, the data follow sort of classic Palmer scaling theories. Okay, so putting a knot changes relaxation times. And what that means is if I take this same molecule and I put it into fields, and I start decreasing my field, it'll actually pass through this phase transition faster. And that's essentially because its relaxation time is different than that unknotted molecule. And so I can do this with all sorts of knots. And basically, if I redefine my field with the proper relaxation time of the molecule at interest, I can collapse all my data together. Okay, so knots make things relax quicker. But knots are not static objects. And this has been quite intriguing for us. So knots can move around on a molecule. And the way we believe they move around, here's a simulation, is actually through a self-reptation. Okay, so they can, if I look at the so-called chymograph, so here's a molecule, and this is time, and I basically turn my molecule into a 1D representation of fluorescence, you nicely see the molecule stretched, and this bright band is actually the knot moving towards the end. Okay? So this is actually a convective motion because the field is going in this direction and that direction, so it can flush off the knots, and that's seen in simulations we do too. Or if our field is slightly smaller, and depending on the type of knot, it will actually diffuse, and we can calculate a diffusion coefficient of the knots. And so if it can diffuse, actually, we can watch how knots untie. Okay, so how the knots untie is not through some global process where the chain swells and it comes off. It actually finds the end of the chain, and then it doesn't necessarily come off all at once. In fact, what we can see is that it'll get near the end, and it's a stochastic process, and it might actually release some of the contour. So it basically changes to a less complex knot. And in fact, both in experiments and simulations, we can watch this process. And we can look at statistics of basically how you go from a highly knotted conformation to an unknotted conformation, and whether that's actually one step or multiple steps. Okay, so unknotting is not just a one-step process. The other thing that's kind of funny that happens in the experiments, and we thought it was something wrong with how we were doing them at first, is actually as the knot gets near the end of the chain, you can see it here, the chain stretches in this direction, and you'll see that it's getting smaller. Okay? I'm not changing my field or how I'm pulling on the DNA, but also you'll see that this streak here gets brighter. And basically the tension near the ends of the chain is less, the knot swells, and so the chain's relaxation time keeps changing and changing, becoming smaller. And so it actually stretches less. So it goes from being highly stretched to a bit less stretched. Topologically, something happens. It has more contour, it has a longer relaxation time, and it stretches again. And it can do this through multiple cycles. So this is the chain, another chain. I'm keeping my electric field constant, how I stretch it, and it goes through these huge oscillations where it's basically changing the type of knot that it has. And so it's essentially an inverse phase transition. Here's a very dramatic effect where basically this is a pretty big knot. When it gets near the end, the whole chain will actually go back to a coil. It'll sit in that coil until part of the contour gets relieved, and then it'll stretch again. And it might still have part of the knot on it. And we see the same thing if we do simulations. It's not quite as dramatic because these knots probably have a lot more contour than we can simulate in a simulation. And why this is basically happening is because if you believe that everything is dominated by this dimensionless group, if I think about the knot size in these series of images, my knot's sitting in the middle, it's pretty small because it's high tension. It starts diffusing, starts getting near the end. You can see it's getting brighter. So actually, its relaxation time is changing. So this parameter is becoming smaller. Gets near the end, it swells more. And then this is actually a critical phase transition, so it can actually compact into a coil for a while. Then we presume it'll diffuse off, and then actually the molecule stretches again. So we think it's interesting that we can actually now at a single molecule level begin to probe and look at single knots and see how they move around. So knots can also jam. Okay, so we kind of know this from macro scale knots that we put in all sorts of objects, right? If we pull tight enough on our laces, we're not going to get a knot to easily glide off. And we can show that in simulations, and the little bit of physics that you need to put into it is basically having some sort of model in which the chain is not smooth. So any sort of corrugation in your interaction energy, if you pull on a knot tight enough, you can get trapped in some local well. And so with the simplest model, just a chain with a series of beads and different bending energies, we can make all sorts of different knots. We can look at how they diffuse versus how we're pulling on them. And we always see that essentially there's a regime where it doesn't really care about tension, but then this is on a semi-log plot. We have drastic slowdown in dynamics, so very glassy behavior. And essentially the knot has to hop around. Basically, this looks like a very corrugated landscape, and it really, to move, it's a very slow time scale. And it's because of the corrugation in the chain. Okay? And this is obviously very, very simplified, right? I mean, there's no way that my DNA interaction landscape looks exactly like this, but the basic idea is that when you get down to molecular length scales, the interactions are not just homogeneous in your linear space. So we can do this in an experiment. So we can take a molecule, and we can actually, in this case, have two knots. And we have it at a certain field. My knot's moving around. And then I can suddenly change my electric field. And what we can actually show is that we can have knots which are initially starting to convect near the end of the chain. And when the graphs turn red, I suddenly turned up my electric field, and I can actually pause the motion. And we can systematically do this at threshold field strengths. And so we can actually turn what was a diffusive process now into a static jammed process. And so we're pretty excited about this because there's been controversy in the literature about whether even you can have jam knots on molecules in general, or particularly on DNA in new nanopore sequencing experiments. So in the past year, my postdoc has basically been able to show a lot of interesting dynamics of knots on a single molecule. So if we look in time, we can have jam states if we have high enough fields. The knot really doesn't do anything. In some conditions, we can get clear diffusive movement. In other cases, we can get convective movement, basically biased diffusion towards one of the ends. And if we're patient enough and look at molecules that have multiple knots, we can actually begin to understand knot interactions. And so, for example, it's predicted that if you have two knots which are actually factored or separate from one another, is that they'd actually prefer to be together. And so we can actually see that this is a good example. You can see in a pretty short time scale, this is real time, the knots are actually have some potential of mean force that actually draws them together. And we see this time and time again. So hopefully I told you a couple of simple physical stories about knot experiments. We're trying to study them a single molecule at a time, mostly being motivated by experiments. If we want to look at knots, it's useful to have a way to make them. And so we have a very simple way that we can make them. We can do this in large microchannels. We can do this in nanochannels, et cetera. So it's quite facile and easy to do. We know that knots will affect actually polymer dynamics, in particular how molecules relax. And then in effect, it'll affect how they move in flows and fields. And in particular, how knots actually disengage from molecules. And the important thing, too, that I didn't have time to tell you is that the way in which knots move off a molecule, either in a field or even in quiescent conditions, is always through a diffusive motion. So it's not through a global swelling of the chain. It's actually finding the end of the chain and then releasing some of its contour. And we're quite confident of that through all the experiments we've done. And furthermore, depending upon conditions, you can have really a wide range of dynamic behaviors. You can have these glassy, basically jammed things. You can have them diffusing, convecting, or you can actually see knot interactions with one another. So I kind of went over briefly some things. A lot of this is actually in publications. All the stuff on the convection of knots we haven't published yet. It's in review. So with that, I end and happy to answer any questions. Thank you.
Go ahead.
In microphone.
Thank you. I know nothing about knots except for fishermen's knots.
Yeah.
But I really wonder, DNA is a stiff molecule, and it's a charged molecule.
Yeah.
And this, in some ways, contradicts what you said, for instance, like two knots willing to join, for instance.
Yeah.
So what can you tell us about that? And the other small question is, how did you image them, your DNA molecules?
So imaging is the quick answer. We just use a random intercalator and just do fluorescence microscopy. So part of the question you're asking is kind of related to this question, which goes back to Dijen, which is basically, right, if I have a chain which doesn't like to bend, why the heck would it want to do this?
Right.
Right? Okay, so here's the argument. So this was put forth actually by Grossberg and Rabin, and then we proved in simulations that actually these free energy arguments are correct. So there are two competing effects. So, right, bending says that you don't want to do this, right? Because you have high curvature. However, what a knot does is it's kind of like being in a polymer melt, where you have a virtual tube, right? You have some limited degrees of freedom for the chain, right? And so how much of the chain is affected is basically the red portion, or how much of the chain is in the knot. So the chain doesn't want to have a lot of it in this tube, this self-confinement, right? So that is saying, actually, I want to have the knot as little contour as possible. This says, well, I want to have easy bending, right? So they have different scalings with actually how much contour is in the knot. And so just balancing those is going to give you a minimum. And if we do actually simulations and look at the free energy, we get a very nice defined minimum.
Does it take into account the charges that you have to bring together?
Yeah, so basically this will get, we've done the same thing with varying charges. And basically we're at moderate salt conditions. So the effective width of our DNA is about 2.5 nanometers. And this will shift slightly as you continue to change the excluded volume. You still get a very persistent local minimum, a big tail, and it continues to go up even to pretty large length scales. So it's really counterintuitive. Yeah.
Have you looked at any effects of the ionic conditions, and in particular presence of multivalent ions that may even compact DNA?
Yeah, so not multivalent, though we should. Though we've done this with different moderate degrees of crowding agents, right? Because I don't know, at least in my hands, trying to do the imaging and not get things to stick, et cetera, with a lot of the divalents, it's kind of a nightmare. But certainly we can increase the propensity of the knots with crowders. The interesting question, which we want to go back, these are really hard experiments to do. I probably wouldn't have the patience to do them, but these images of actually watching a knot diffuse around, you have to be very patient. And so basically what I want to do is look at how this size and diffusivity changes with ionic strength. And that should have a strong effect related to what we were just talking about, right? Yeah.
So I also know pretty much nothing about knots, but I find that phase transition fascinating. That when the knot gets towards the end, so the
right.
whole DNA sort of becomes a coil. So can you give a sort of brief hand waving, sort of bend-in versus entropy argument as to why this happens?
Yeah, well, so I can tell you in general, if you don't have a knot, why it happens. Okay, so it's basically that you can describe, right, we saw force responses of DNA earlier. The initial force response is a linear spring. And you can describe these fields by a potential. And actually, exactly at this dimensionless field strength, your energy landscape is pretty much flat for all fluctuations. And it's only normalized by the fact that the molecule is a nonlinear force response. So it would want to just fluctuate all over the place, and then it gets normalized. So essentially, a spring constant can be translated into a relaxation time with a friction coefficient. And the knot is changing dynamically as it moves along, essentially my spring constant of my DNA, to the point where actually it's just such that I have the right spring constant to go to be subcritical. So it's the fact that actually it's not a single relaxation time. It actually depends upon where I am.
Okay, I was wondering, because you mentioned about the salt and this thing. Have you considered to do kind of stop flow experiments? Because if you do a stop flow, you could have two going in, and then you could see with small angle scattering, for instance, neutron scattering or so, and then you could see what's happening on the structure. Then these are in a way different flow rates and so on.
That's a great idea. anybody else who has ideas about higher resolution, I'd be interested to see and talk to you if we'd have enough resolution actually to see that. But yeah, we were very curious about actually what is inside what is the topology of the particular knots we were making. Great idea. Yeah, Aaron.
So very nice talk. So far, you've mostly considered comparisons between knots versus no knots, right?
Yeah.
How should I think about the taxonomy of knots, right? Would there be a way of reconstructing some kind of knot equivalence based on the behavior that you see and so forth?
Yeah. So right. So there's mathematically. There are lookup tables, and up to a certain number, basically if you project a string on the ground, you can look for the minimum number of crossings, and there are lookup tables, and for a certain number of crossings, you can have a certain number of differentiable knots, and that grows exponentially, and up to 10, 11, it's been enumerated explicitly. Okay, so that kind of exists, right? And if we actually had high resolution imaging, we might be able to get to that. We don't have that, and so we've invented through the nanopore stuff, I don't know if I have it as backup, we've tried to come up with ways, like nanopores have much more detailed information. We actually can get very nice, highly resolved information about how much contour is stored in these. And so we basically have come up with rules of digital signatures of these events. And the nice thing here is that in a nanopore, the PhD student can get like 5,000 events in an afternoon, versus when we do this a molecule at a time, right? I mean, we get 20. So we have a library now of those, and we're trying to think which one of those could possibly map up to certain ones in these knot tables. So that's our strategy. It's a very difficult topological question, but.
Okay, I don't think any more questions.
I think I can speak. During your talk, you mentioned that the spherical confinement can enhance knotting.
Yes.
And in your answer to other people's question, you said confinement. Are they same, or when you said the spherical confinement, that's spatial confinement? And this case, you described in a kind of chain entanglement, which confines somehow.
Right.
Are they similar effect, or something you are talking something a bit different?
Two different things.
Yeah.
So one, I'm saying essentially if I constrict my whole chain to be, say, in a sphere of a certain volume, and I keep decreasing that sphere, what is the probability that I have a knot? And that goes up to nearly unity at some point. A different question is if I think about my DNA as a space curve, I can always start chopping off the ends until mathematically I change the topology and say, that allows me to say, where is the knot? And so the fact that it's spatially confined to a local region along the contour is the second question about the energy profile. So they're really two separate things. In terms of the free energy arguments, they're very related, but they're separate and distinct.
Thank you.
Yes.
Okay, I bet I have one simple
Oh,
question.
sure. Yeah.
What about using Polyelectrolytes
Yeah.
to remove the knots?
Yeah, now that we're good enough at holding them for a while, I think we could. But we weren't very good before actually at making them, and then actually doing those experiments where we watch them move. Yeah, we'd love to do that. Yeah, great idea.
Okay, thank you very much.
Yeah.
Let's thank the speaker.